Oh, hey, how's it going? I didn't see you there. What is the universe made out of? As far as we can tell, it's made out of stars, planets, galaxies, and everything else that can kill us with a single blow. But the universe is dark. Darker than we think. And to know exactly how dark it is, we have to go on the greatest journey in the history of YouTube videos. The quest for dark matter. For this incredible journey, we need to start at Caltech, where in 1933, Fritz Zwicky examined the coma cluster. He found that the galaxies in the coma cluster were moving too fast to stay together. They were moving at about 1,000 kilometers per second relative to each other. This is too fast for them to stay gravitationally bound. So the puzzle remained. Why was the coma cluster still there? There were 4 possibilities he considered. Stars in the coma cluster behave very differently than those in the Milky Way, emitting much less light at equivalent mass, or the coma cluster is not in equilibrium, or the laws of physics are different here and in the coma cluster, or the coma cluster contains lots of additional mass which doesn't emit light, dark matter. In a 1937 paper, he considered all these options, but especially number 2 and number 3. But now, almost 80 years later, number 4 dominates. There's simply not enough visible mass to keep the cluster together. There was some sort of matter there that didn't emit light, but we knew it was there due to its gravitational influence. For further research, let's talk to Vera Rubin at the Carnegie Institute of Washington. After Zwicky, there was a raging debate in the scientific community on how galaxy clusters stay together. Vera Rubin wanted nothing to do with that. So instead, she decided to examine individual galaxies. Picture the solar system, the sun in the middle, and all the even more insignificant balls of rocks and gas orbiting it. Mercury, the closest planet to the sun, orbits once every 88 days. Venus, about 225 days. Earth takes a year, and each successive planet takes longer to complete an orbit. Rubin figured the same rule should apply to galaxies. The further away a star is from the galactic center, the longer their orbital period should be. However, Vera noticed that the stars at the edge of the Andromeda Galaxy and all the other spiral galaxies that she observed were moving too fast. Their speed remained almost constant while the distance to the center increased. So, just like the coma cluster, it didn't make any sense. The stars at the edge of the spiral galaxies should have flown away by now. There wasn't enough mass to keep them in the galaxy, so the mystery remained. There was some extra mass there that we couldn't see. But lucky for us, about 50 years prior, Einstein developed his general theory of relativity. It was the first theory to describe the geometry of the universe, how matter can bend space, how mass can bend light around it. Just like the lens in your glasses, enough mass can magnify the things behind it. This effect is known as gravitational lensing, but Einstein said we would never observe it. Lucky for us though, he was wrong. This is an image of a galaxy. The long horseshoe shape in the middle is one galaxy behind the galaxy in the middle. The light curved around it to produce this. But has this effect been observed with dark matter? Why yes it has. Here's another image of one galaxy, 5 billion light years behind the foreground ones. Oh, you don't see it? Well, it's right here. And here. And here. And here. And some other places as well. The dark matter cluster is more or less a giant amorphous blob, so the light from the galaxy behind it curved in different ways around it. This helps us quite a bit, actually. We now know that the only force that dark matter seems to interact with is gravity. So we know it has mass. Does it have a charge? Or a spin? Is it even really a particle? Well, that's why we gotta keep searching. Of course, since dark matter doesn't interact with electromagnetism or the strong and weak nuclear forces, if I tried to hold some in my hand, it would fall right through and plummet to the center of the Earth. Plummeting. What if we built an experiment underground? It's hard to take measurements out in the open. Well, with all the cosmic radiation and all. But underground, we don't have to worry about that. So we have experiments all around the world testing just like that. Although it doesn't interact like anything we've ever seen, maybe it's just a WIMP, a weakly interacting massive particle. Currently, it's one of the last normal matter candidates for dark matter. Just like dark matter, they wouldn't really interact with anything outside of the gravitational force, and possibly a fifth similar to the weak nuclear force. But it's still a mystery. So how about you all follow me to the dark side? 50. Just 80 miles east of Rome, at Gran Sasso National Laboratory, 1,400 meters below the surface of the Earth, is this experiment. Dark Side 50. Inside a house-sized tank, a large metal sphere holds a particle detector called a scintillator. This container is filled with 50 kilograms of liquid argon and a thick layer of the element in its gas form. If a dark matter particle comes in and hits the argon, the recoiling atom gets a kick of energy and it quickly tries to get rid of it. In argon, it gets rid of it by kicking out light. It sheds photons. But it also loses some charge, and those electrons drift up into a gas layer, and when they hit the gas, you get another flash of light. So far, their experiments have been inconclusive. Everything they found could be explained by a neutron. But let's keep going. In 2009, CDMS researchers found two potential candidates for WIMPs. They concluded that there was a 23% chance that they were wrong. It's certainly not anything you should throw all your chips into, but it's not something we should ignore. These underground searches are more direct though. Is there any indirect way we can sense these? Why yes, viewer, yes there is. My absolute favorite one though is the search for dark matter in the sun. Let's head to Suwon, South Korea. The evidence that a yet-to-be-discovered new particle, denoted as chi, could explain the dark matter in the universe is compelling. A high-energy neutrino flux from the sun is a smoking gun signal for confirming the particle nature of dark matter. When dark matter gets captured by the sun and self-annihilates in its center, high-energy neutrinos are expected to be generated in prompt decays of the dark matter annihilation products. As the sun travels around our galaxy, it picks up dark matter along the way. This dark matter falls to the center and clumps up. Once it reaches a state of equilibrium, however, some neutrinos will be produced with pions and kaons. In such decay, we will be able to detect neutrinos with energies much higher than normal. Once we find it, we have confirmed WIMPs and probably a new fundamental force. But it's possible that dark matter isn't a WIMP at all. We could be way off base. It could be a string. It could be explained by brown dwarfs or neutron stars. It could really be anything that we haven't yet even begun to describe. But all the other options that we've tried, aside from WIMPs and a couple others, have been weeded out over the years. But maybe there's one more thing we can do. Let's try to make some. Let's head to CERN. CERN is where the Large Hadron Collider is.
Large Hadron Collider? I just met her.
God damn it. The LHC smashes particles together at near light speed. When they collide, particles spew out in damn near random directions, and sometimes we find a new one. Like, let's say, for example, the Higgs boson. The point of the LHC was to simulate the early universe, so theoretically, the LHC could create dark matter too. Of course, it would just fly through the walls of the collider and fall down to the center of the Earth. But that means there will be missing energy in the reaction, and that's something we can calculate. This entire time, I've been neglecting talking about dark energy, and that's something totally separate from dark matter. It's an even bigger question. But in the end, we're left in the dark, alone. But there's no need to be afraid. Keep searching. If you like the content, please consider dropping a like and subscribing. Check us out on Facebook and Twitter, and be sure to share if you learned something. We'll see you next time.
Yeah, it's just as you assuming it's nothing but these humans who like to blame mythology for everything they're doing. They pray for non-existent gods to clean up the mess, but never take responsibility, just claim it's a test. See, that religion you've been given is shit and it's all poison. And it's partially the reason we bleed and it's all poison. Your worldview is poison, your outlook is poison. You can deny it all you want, but the truth is it's all poison.